All right, guys, it is time for section 6.4, nth roots, and we are extending what we know about square roots to talk about things like cube roots, fourth roots, fifth roots, sixth roots, and so on. So this is an important section. We talked last time about graphing square root functions. Today we're not really talking about functions, we're talking more about simplifying radicals like we did back in chapter 4 when we talked about imaginary numbers. So doing that exactly, and then also sometimes we're going to use a calculator, especially when we use it in a real life situation. So vocabulary to be on the lookout for: nth roots, radical signs, you should know what that is, index, radicand, and principal root. So make sure that you understand what those are as we go through this presentation. Okay, so as you know, square rooting a number and squaring a number are inverse operations. So that's why if I have the square root of x equals 4, I square both sides. Why? Because squaring a square root is an inverse, and that gets x by itself, right? So squaring and square root are inverse operations. That can be true for any kind of root. So if I have a cube root, then cubing a number is the inverse operation. If I have a fourth root, taking a number to the fourth is the inverse operation. So just like with square roots, if I want to find the square root of a number a, I need to find a number that I can square to get a. So what is the square root of 16? It's 4. Why? Because 4 squared is 16. That's the relationship. So this works for cubes, fourths, fifths, etc. So here, x cubed is 64. So what is the cube root of 64? Well, it's 4. Why? Because 4 cubed, 4 times 4 times 4, is 64. So a perfect cube root has to have 3 identical factors. Same thing with fourth roots. If I'm looking at 625, well, 5 to the fourth is 625. That means that the fourth root of 625 is 5. It works the same with fifth roots. What's the fifth root of 32? Well, 2 to the fifth is 32. So the fifth root of 32 is 2. And that's true of any root. So we can call those nth roots. So a is the nth root of b if a to the n is equal to b. Okay, and that's what this definition here says. If a to the n equals b, then a is an nth root of b. So for example, negative 3 to the fourth, inside parentheses, is 81. So negative 3 is a fourth root of 81. And positive 3 would be its principal root, because 3 to the fourth is also 81. We're going to talk a little bit more about principal roots here in just a second. So remember what our vocabulary is for these things. The symbol, the radical sign, is called a radical sign. Looks like the square root, but we can change the index, right? So when it's just written like this, there's actually an index of 2. When it's a square root, we just don't write the index of 2 because that's the most common kind of root. So if I have an index written there, it tells me what kind of root I'm looking for: cube root, fourth root, fifth root, and what's under the radical sign is called the radicand. All right, so here we go with the principal root thing. Some numbers have more than one root. For example, we know that 64 has 2 square roots, positive 8 or negative 8, right? Because 8 squared is 64 and negative 8 quantity squared is also 64. When there is more than one root, more than one real root, and n is even, so n is the index, right? When I have an even index and there's more than one real root, then we have to choose which one we call the principal root. So which one is like the main one. The principal root is going to be the non-negative one. So for example, when I talk about the square root of 25 being 5, if there's no negative sign written here, I assume that I want the principal square root, which is 5. If I write the negative sign there, it means I want the opposite of the principal root. So I want negative 5 instead of positive 5. And sometimes you'll see plus or minus written, meaning that they want both square roots, okay? So the principal root is the positive root if there's more than one root. But, for example, like on the last slide, we looked at this cube root of negative 81. Actually, I'm going to change that to the cube root of negative 27. That's negative 3. And negative 3 is the only cube root of negative 27. There's not more than one, and n is odd. So there's no positive root here to put as the principal root. So in this case, negative 3 is the only cube root of negative 27. Okay, so in that case, we don't have more than one. It's only when n is even and we have more than one row root that we talk about principal roots and opposite of principal roots. Okay, let's look at what we're talking about here. Here we're still thinking about nth root of a, where n is the index and a is the radicand. Okay, so we have to think very carefully about what happens when my index is even and when my index is odd. So let's focus on an even index first. So this is like square roots, fourth roots, sixth roots, so on. If a is what is underneath the square root or the radical sign. If a is positive, then I'm going to have one positive and one negative root. So this is like taking the square root of 25. Plus or minus 5 are the two roots, and positive 5 would be the principal root. If what's under the even root, square root, fourth root, sixth root, is negative, there are no real roots. That's like taking the square root of negative 4. We know we can say plus or minus 2i, but those are imaginary roots, not real roots, right? And if the number under the even root is 0, it only has one root, which is 0. Okay, so these are things we already know. We're just extending them beyond square roots. If my index is odd, so here we're talking about cube roots, or fifth roots, or seventh roots, or however far we want to go. If a is positive, right? If a is positive, there's one positive root, no negative roots, right? So this is like the cube root of 27. That could only be 3. If a is negative, there's no positive roots and there's one negative root. That's like we just looked at the cube root of negative 27 is negative 3. Why? Because negative 3 times negative 3 times negative 3 is negative 27. That's the only possibility. And again, if what's under the cube root or fifth root is 0, then 0 is the only root. Okay, so you might need to take a little time to go back and read back over those charts and make sure that you get all of the concepts. If you have questions, bring them to class. But let's try finding some roots. So here, we're going to simplify plus or minus the square root of 16x to the 8th. This is like something we did in chapter 4. Notice the plus or minus means we want both the principal and the opposite of the principal root. So basically I have to think, okay, well I know that 16 is 4 squared, and x to the 8th is x to the 4th squared, which is what they're showing you here. So the square root is going to be plus or minus 4x to the 4th, just like we did in chapter 4. That would be my final answer. That's the principal root would be 4x to the 4th, and the opposite of the principal root would be negative 4x to the 4th. Okay, take a look at this one. I want to find the opposite of the principal square root of q cubed plus 5 to the 4th. Now be careful here. Notice the q cubed plus 5 is inside parentheses to the 4th power. Right, so really I'm taking the square root of something to the 4th power. Well, I know that something to the 4th power is, in this case, q cubed plus 5. That's q cubed plus 5 squared, Just like if I have x to the 4th, I can say, okay, that's x squared, right? So the square root of something squared, the square root of something to the 4th is something squared. So the negative comes from the sign on the outside. Then I just have q cubed plus 5 squared. And that's my final answer. I can't go any further than that. Okay, let's look at this one. Here we have an odd root. So the 5th root of 243, a to the 10th, b to the 15th. Tomorrow in class, I'm going to give you a chart of common cube roots, 4th roots, and 5th roots that you need to be familiar with. And you'll see on that list that 243 is a 5th root. 243 is 3 to the 5th. You can also investigate that with your calculator a little bit. A to the 10th is a squared to the 5th. And b to the 15th is b cubed to the 5th. So when I take the 5th root, I end up with 3a squared b cubed. And that would be my final answer. All right, let's look at this one. This is a throwback to chapter 4 as well. There are no real roots here because it's a square root of a negative number, right? Negative 4 does not have two real numbers that when multiplied together give negative 4, but we know from our work with imaginary numbers that 2i and negative 2i would be the imaginary roots. Okay, I want you guys to try these next 3 examples. Okay, this one should be plus or minus 3x to the 4th. Try this one. Okay, here your answer is A. You're taking the square root of something to the 8th, which is going to be that something to the 4th, and then the negative is what they ask you for. They want the opposite of the principal root. And part C, a 5th root. All right, your answer here is 2. This is not a plus or minus situation. It's an odd root. 5th root of 32 is 2. 5th root of x to the 5th is x. And the 5th root of y to the 10th is y squared. Okay, this is an important thing that's a little bit different than what we've talked about before. When you find an even root of an even power, okay, so like the square root of x to the 6th, let's say, and the result is an odd power. So if I take the square root of x to the 6th, that gives me x cubed. The result is odd. I have to do the absolute value of the result to ensure that my answer is not negative, okay? Because since I don't know what's happening here, right? X could be negative, and if x is negative and I'm taking a negative number cubed, I would get a negative answer from a square root, right? Without the negative being in front, and that can't happen. So if I have an even root of an even power and I get an odd power, you have to use absolute value. Remember that if my index is odd, so if I'm taking an odd root, there's only one real root, so there's no need for absolute value to make sure that I'm getting the principal root. Okay, so let's look at this. The 6th root, so an even index of t to the 6th, even index, even power. What's my answer? It is t to the 1st, right? The 6th root of t to the 6th is t to the 1st. T to the 1st, that's an odd power. So I have an even index of an even power and I get an odd power, so I have to use the absolute value of t to make sure that I'm identifying the principal root, the non-negative root. All right, take a look at this one. Here I have a 5th root of 243 times x plus 2, that quantity to the 15th. Well, what's the 5th root of 243? It's 3. And the 5th root of x plus 2 to the 15th is x plus 2 cubed. The index here is odd, so I don't have to worry about absolute value. This would just be my final answer. Again, cube root of 243 is 3. The cube root of something to the 15th is that something to the 3rd power. All right, I want you guys to try this. Okay, hopefully you noticed here that you're taking an even index, even power, and you get an odd power x to the 1st, so you have to use absolute value. All right, try this one. Right here, since your index is odd, we don't have to worry about absolute value. The cube root of 27 is 3, and the cube root of x plus 2, that quantity to the 9th, is that quantity of x plus 2 to the 3rd. All right, let's take a look at this real-world example real quick. I'm going to pause the video and take a second to read this through. All right, so hopefully you notice that D is the diameter of the hole, K is the energy in joules, and notice the relationship involves a cube root, okay? So we're going to estimate the diameter of a hole, so we're going to estimate D, we don't know D, created by a particle with 3.5 joules of energy, which is K. So we're going to plug that 3.5 into our formula. I'm going to substitute it, and then in this case we would use a calculator to evaluate it. Get excited about that. So we plug in our 3.5. You just have to make sure that when they give you information, you're plugging it in for the right variable. And then you use a calculator and you get about 1.237 millimeters. Super important that you read the units and put the correct units in the answer. All right, and when we check, if I wanted to plug in the answer that I got for my diameter and solve for the energy, I do get the energy that it gave me at the beginning. So that shows that my answer was correct. Okay, this is the same problem, but this time they're saying if a hole has a diameter, so this time they're giving me the diameter of 2.5, estimate the energy. So this time I have to solve for K. I plug 2.5 in for the diameter. I add 0.169 to both sides, divide by 0.926,